Hi, welcome to Module 4. We're going to look at what's new in maritime positioning. In particular, we're going to take a look at L2C, the new GPS civilian frequency that was previously the encrypted military frequency. And now we have a new frequency that we can harness to get us differential positioning accuracy from space. And we're also going to look at LiDAR, a new technology that creates point cloud navigation, which may very well be the future of maritime charting and navigation. We'll dive right in. So space-based positioning is now called GNSS. It's not just GPS, although we're going to focus on the new L2 frequency from GPS. GNSS is the global navigation satellite system composing our US GPS, Beidou from China, GLONASS, which is the well-established Russian satellite system, and Michelangelo from the European Union. A lot of the receivers that I see pilots using with their pilot carryboard units are able to track more than just the differential GPS, or rather GPS from the US. They also can track typically GLONASS and Beidou, and some will also pick up Michelangelo. So those are our base new frequencies that are out there. Lots of satellites. So many of you have seen this chart before. It was put out by the Department of Defense about the modernization of GPS, which the military is very concerned about and really wants to have their M high-powered GPS and their L5, which are bundled onto the new satellites that have been pushed up into space in the last 10, 12 years. We needed about 18 full operational satellites for FOC, full operational capability, in order to roll out L2. L2, if you see on the chart here, some of the words are kind of, like a lot of things, there's a bunch of acronyms, it's kind of cryptic, but CA means Course Acquisition Code for the L2 signal. L2 was the military's encrypted signal, but now it is going to be a civilian version called L2C, and we would be able to link into our conventional L1 signal from the GPS and get the L2C signal, which has a better anti-spoofing. It is higher power, so it's more difficult to jam. And because we have two separate frequencies raining down from space through our atmosphere, we can make an assumption about the delays on each of those through our atmosphere and cancel the atmospheric error, which is about 50% of the GPS error budget. So L2C has great promise, and it's going to really, when it's deployed, it's believed that L2C is going to give us differential accuracy from space, sub-meter GPS, reliable GPS positioning from space. That's the big hope. So like in the previous slide, you saw that all those satellites were supposed to have been deployed by 2020, and we're on the eve of 2023, and it looks like we've just got there, right into that 18th and 19th satellite are coming online right now that have the L2C capability. And if you'll notice, this is a GPS World magazine article from 2015 saying that we will have L2C in 5 years, and now it's in the 8th year, and we're just starting to get it. There's been a lot of delays in our space program in order to launch these satellites. They do require, they're a big satellite in the 14,000 pound range, or a little less. I mean, they're one of the largest payloads we put into space as far as satellites are concerned, and they're very expensive and difficult to manufacture. So, yeah, Northrop Grumman is the lead contractor on them, and good deal. We've got L2C now on the hook. But I want to show you, I went to gps.gov today and also the FAA's website in order to get the latest horizontal, rather position dilution of precision chart map for you, so you can see what the PDOP is for L2 and the official statement on the use of it. So let's look at that next. Okay, here's the current GPS signal position in space, dual frequency, L2C position dilution of precision chart for the world. So this shows that if you have a GPS that is tracking L1 and L2 currently today, and I pulled this up, it's updated every 3 minutes, and you can go to that website at the real-time WASP website at the FAA, post these signals up because aircraft users are very keenly interested in L2. The WASP test team, which is the Wide Area Augmentation System, which is our current space-based augmentation system to improve GPS accuracy for en route navigation of aircraft, but we do use it here on our maritime domain because it's accurate and it gives us a sub-meter fix generally based off around 2 to a maximum of about 4 satellites, which are often leased, of course, from the Inmarsat Corporation, and they are geosynchronous satellites, so that's WASP. But our chart that we're looking up here is not about WASP, even though it's put out by the team that monitors WASP. This is their new competitor to WASP. This is the L2 civilian frequency. We're waiting to come to fruition. And here, if you look on the map, you'll see that there are dark red areas. Those are bad areas, like down there around Easter Island. Of course, there's a hole in it, right? And this map moves because these satellites, as you know, they make 2 laps around the Earth every day, and they're not in geosynchronous. They're halfway there, so instead of being 4,000 miles away from the equator, they're out there around 12.5, and around 12. Actually, it's 11,800 miles is where our GPS satellites sit in their orbit, which causes them to do 2 laps a day around the Earth. And they're in 6 orbital planes. So these 6 orbital planes each have 4-ish satellites in each orbit. These guys are zinging all around the Earth, and therefore their coverage map changes as they sometimes will cluster up into one area, and you'll get too many satellites all bundled up in one area, and then they'll get all evenly distributed. And they do their best to maintain and manage this, but regardless, we always are going to have some coverage difficulties because we only have 6 orbital planes, and as of this morning, we have 30 satellites. So that's about 5 per orbital plane. And you'll see here in the Caribbean, we've got this weakness here, which says a PDOP level of 5. And PDOP, just like HDOP, which is horizontal dilution of precision, PDOP is the algebraic addition of horizontal and vertical dilution of precision. So VDOP plus HDOP equals PDOP, position dilution of precision. So this is the grade on how potentially accurate your GPS fix is going to be based on the geometry of the satellite network that it's going to be looking at. And of course, we know as mariners, if you were taking a star fix and you had your lines of position and you had a really big triangle, then you had a lot of ambiguity in the middle of the triangle as to where you might be. Same thing here with satellites, except that we're using spherical trigonometry to make spherical LOPs, so they're like a bubble, an edge of a bubble, and if that crossing angles are too acute or the spacing amongst them are too wide, then our position dilution of precision will gain up, which is what you see here in the Caribbean of around a 5. Anything 6 and higher is unusable. It really goes up to a level 12, which we've never, it's unusable. Good PDOTs, which are below my face, they're down here in this part of the chart. That dark blue part of PDOPs of 1 or 2 are really good. And so we have on L2 really good L2 coverage right now in mainland, CONUS here in the U.S. But hey, it could change, right? Because satellites are all moving around and those coverage gaps might happen. But right now, if you look at it, if you're an L2 user, you probably got good coverage. And 1 or 2 more satellites will have enough redundancy, resiliency for our government to say, yeah, for sure, it's time to use it. But look at the notice right now from this morning, which is up next from GPS Gov, about their official position on L2. Yep, for sure. So go to gps.gov. Their official position on L2 is that it's pre-operational. It does work. It has good numbers, but It lacks resiliency because it doesn't have enough redundancy. So its sustainability is low, or it's not ready yet. So if you have a safety of life or a critical purpose, like guiding a big tanker or a cruise ship down a narrow rocky channel, then that's considered critical, right? You are not ready to use L2C or the L5, which is a safety of life signal. And it's also higher frequency, more power, difficult to jam, more precise. We're waiting for it. So we're this close to be given the full green light on L2. But as pilots, we should start looking to the future. This is the time to start testing it. This is the time to get your advanced GPS providers to commit to an L2 solution and allow you to chart it and check your position against it and switch between L1 only and L1, L2 and see if it changes your position on the ship. And let's start getting some operational guidance and operational experience. Even though it's in a pre-operational status, there's no reason why we can't start testing it. So it's going to be good. L2 is coming online. Good on it. Okay, let's switch gears. Talk about LiDAR, which is laser ranging and detecting. It's a British acronym, which the British are kind of fast and loose with their acronyms, right? Like radar is radar, detection and ranging. So instead of each letter being the first letter of a word, they just hodgepodge it together. So that's your English is fast and loose. The English are with their acronyms. Okay, well, good. So we're in LiDAR. LiDAR is cool. I think you're going to like this. Well, if you really want to learn about LiDAR, just go down to your high school where they're doing those robot races and they're training the kids to make robots and do simple coding. And you'll find that almost every one of their robots has a $40 type LiDAR like you saw right here that you can buy on Amazon. It's a little module that goes on an Arduino computer. It's easy to program. It's got one, the laser comes out of one and it gets received by the other, and it can determine the range to objects. They use it for obstacle avoidance, and they train the robot, to go through mazes and things. So this is where you'll see LiDAR is really common right now. It's a normal piece of gear all over the world. Matter of fact, a lot of cars' backup sensors are LiDAR. Some are ultrasonic, right? We know that, they use sound waves, but many of them are also a laser ranger, and they have laser rangers around the car, like Teslas and other cars like this have sensor packages. They're using LiDAR as one of the sensors. So hey, getting away from the kids at the high school that are using LiDAR, let's talk about the pros. Here's one of the big companies, Inertial Labs. They make a lot of equipment for remote positioning, for scanning, for sonar, sell a lot of gear to the military, for inertial navigation, and of course they also build LiDAR systems and the software to integrate the LiDAR data. So I thought you might be interested in it if you wanted to go look up one of these companies. Inertial Labs is one of the top ones. When I was in Boston recently and visited Sea Machines, which is one of the top maritime autonomy companies in the U.S., much of the equipment that was on the Sea Machines vessels, which were the positioning gear, came from Inertial Labs. Nice stuff. Here's a commercial maritime unit from England called the Merlin, and it's fitted on the MPA Investigator, which is a ship up in the North Sea. Regardless, the Merlin unit is able to generate high-resolution point clouds of data using the LiDAR system to paint incredible views of our docks, for instance, and cranes and shore systems and fendering, and it gets it all. And if you combine it with the multi-beam sonar data, you get a really immersive look at the maritime domain. Here, let's take a look at one. Hey, look at this incredible picture. This is the amalgamation of two types of data. We've got our multi-beam sonar data, which nowadays we're going to see in our NOAA S102 products, which are are bathymetric attributed grip files, BAGs. And these BAGs are now becoming available to all mariners, and we're going to get this super high resolution sounding data that almost all of our sounding vessels can make it now. They almost all have dual multi-beam sonars. But notice with the sonar gear here, then look at those Yokohamas. The Yokohamas were picked up by the LiDAR. And so the LiDAR, an interesting piece of equipment, right? Like this Merlin unit, you could coast down the whole dock, and the multi-beam sonar is picking up the bottom. And then the LiDAR, it's got these millions of little penetrations of laser information. The lasers zinging in all these little holes and picking up all the structure and bringing that back out as a point cloud of data. And look at it, renders it. You can see the dockside space, the cranes, you can see containers on the dock. You get an impressive three-dimensional data set that's about a maritime dock area. It's fascinating, right? And this is what, when this is mixed with other forms of data, you can co-author it against radar, against ultrasonic information for also cameras. So using the cameras that do a pixel to pixel comparison and are able to screen track things using the camera. And then when those are mixed into a data fusion of information from LiDAR, you end up with a point cloud of information that's kind of timestamped for a certain period. If you come back and things change, you can see the differences. So you can see what changed on a dock. That's really interesting too. There's a lot of interest here. Again, here's LiDAR data. You can see the container cranes, multi-beam sonar data of the bottom, and then there's small self-unloading container ship here. The LiDAR can actually read the name on the container because the paint thickness is different. Picks it up. Amazing, right? I mean, that's the kind of detail that the LiDAR picks up. You can mix the LiDAR information with a thermal camera, and then you end up getting a data fusion between the thermal image and the LiDAR. So one of the futures, certainly for marine navigation, is for ships to be outfitted with this equipment, and it's just passively, as the ship comes and goes from the berth, and if she's a regular caller, I mean, the ship is going to have so much data about their voyages. It's going to be doing pass after pass of the underwater sonar tracks, pass after pass of making a LiDAR point cloud that a computer can go in and append and amend and change, and to basically have built up over time a three-dimensional picture of the port area. And of course, this is going to be a huge boon for vessels that have automation, because they're going to use it to navigate with. But we could use it to navigate with as well. It could help people as well. Okay, let's put on our imagination hat, right? And here's a picture from Inertial Labs where they're talking about how their systems are used to navigate, clearly a cruise ship. And we see this if you're a Florida pilot using your CIQ, you snap the distances out to a fender line. It'll automatically pick up those distances. Well, LiDAR can do the same thing. Here it's an active sensor that's putting an active laser out on a target, and not only does it give you a distance, but it can hook it and track it, and it can feed back to a navigation system to maintain a distance. It's all number of advantages there. Notice over here we got a little small vessel in track in their sensor fusions data system they're showing here. Imagine if that was not just a little fishing boat, maybe it's a towboat, and it's got 20, 30 barges out in front of it. Well, we all know the barges don't show up on AIS. Just get this wee little triangle that shows you where the towboat's AIS is, but you don't see the whole tow package. Well, certainly we know the LiDAR would pick up the entire tow package. It might even be able to count the barges in it. And then if you fuse that data with the radar picture, you could get quite an immersive image about what the actual structure, the profile, the composition of the target is. And therefore you get more information about it and make a better assessment about it. And there isn't a, like, oh, it's just a little triangle, but it turns out to be a huge bunch of metal all stretched out. So you get a better picture. So there's a chance here that these fusion packages are really going to be able to harness the power of the point cloud and provide us a whole new perspective on how to navigate and what's important. We'll see. But it's coming to us soon. It's happening right now. Hey folks, that's the end of our 4th module, and that's the end of my part of this thing where we were going to talk about radar and new tech, and I think we've done our diligence on it. So certainly we talked about radar bands and choices, and we went down the rabbit hole on safety. No, that was a joke, okay? And then we talked about tuning, and we got a little on the basics of analog tuning and looked at these new electronic suppressors that are the electronic magic that's inside the box and whether or not we need it or not. And of course, that led us into a discussion of the suppressors and correlators that are the advanced features on radar. And then we talked about identification on the radar in the sense of the virtual AIS. And we looked at how an example was on the Luling Bridge where, an attempt was made, but we have to really be willing to verify virtual AIS data. And we need to have the radar hit it and correlate it to the target that it's associated with, because just trying to bring the GPS in and orient it to the radar target, there's a lot of play there, and it gets kind of sloppy. So we saw an example of that. Then boom, we went into navigation, talked about indexing, and the idea that if you want to maintain your position in a channel, and you also might want to pose an argument that you're in compliance with Rule 7 on ESO, that there's a good idea at play to put VRMs, put an electronic bearing line out. Say I'm going down the channel. I want 200 foot of buffer on my port side. Okay, cool. Your ESO might be to put an EBL at 200 foot off my port side from my scanner. Let's say I want 200 foot from skin to skin, and I'm on a 106 beam ship. I'm like, okay. Well, I got to add that extra 50 foot of metal, assuming the scanner's on center line. So you had to think about a couple things. Add a little buffer, put that EBL out there, make sure it's in relative, lock it in out in front of the ship, and now you're out using your radar, and you go to meet somebody, and you want to know if they're on their side of the channel. As long as their green stuff that's coming at you in the radar echo is staying to the side of your EBL line, well then you are going to get your 200 foot of clearance. And now you also have an arguable point on Rule 7 saying that you had an equivalent and systematic method to evaluate a target's in the channel in the context of the rules of the road and safety in pilotage. It's a defensible position. You can also use a VRM in that situation that might be like your extremis maneuvering zone or whatever's competent for you to do. You choose, but it's an idea whose time has come. And hey, fast forward into what's new with GPS. L2C. It's out there. It's working. It has good position of dilution. It's getting great reports back. We have enough satellites to make it work. The government doesn't want to say it's ready, but we see it working. But they don't want to say that it's resilient enough to be trusted for safety of life and for high value, type navigation that you're doing. So it's not ready, but it's certainly ready to be tested. So it's high time that we start working with our vendors to make sure we're L2 ready and that we can harness good old US of A GPS signals that our tax dollars have gone hard at work at in the last over 15 years to bring this modernization of GPS to us. By gum, we should use it. We've paid for it. And so let's get it going. And it's a good time to take a keen interest in L2. We can get differential correction level positioning from space without having to rely on a ground sensor like in WAS to measure our local error and then bounce it all the way up to a geosync satellite, bounce it all the way back down to us again. We don't have to have a ground sensor to help us with that. We would be able to compare L1 and L2 from space and get a sub-meter accurate fix for sure. And then lastly, I thought I'd bring you this big story on LiDAR. You know, it's one of the fundamental sensor packages on autonomous vessels. They love that LiDAR because it really shows them what's out there. But I'm intrigued by it just looking at the fabulous images it makes and this concept of the point cloud. Point cloud navigation is really something. And with our S100 series data, which I know we talked about the topology of the bottom and bathymetry with our dual axis Doppler log type data, that's all in this high resolution. That stuff's S102. But we also have other data in the S100 series that could become part of our point cloud navigation, including current and wind and weather and the depths. And there's other things. So we have a lot going on here. And I think the entire root source of navigation is changing right before our eyes. And LiDAR is one of those pieces of technology that's really, it's amazing. So I'm going to be signing off right now. And then Captain Stuart Lilly is going to jump in on the second part of this big day, which is our Bridge Resource Management for Pilots refresher and a case study of 4 hot case studies that Stuart's going to go through with you in the context of pilotage to look at how they relate to our BRM refresher. So awesome. Hey, thank you, and I'm signing off now, and I hope the rest of the day is perfect with you and Captain Lilly. Bye.